Okay, so oops. So we have a disk rotating around a central shaft like this. And then we're going to drop another one. It's even a little bit bigger down on top of it, right? And they're going to spin together. And we're trying to figure out the final angular speed, which is omega. It's a spin rate. So it's going to be in radians per second. But we're trying to figure out what is the final angular speed of the system. So the first thing we're going to do is figure out what is the total angular momentum of the first disk, because whatever that angular momentum is, it's going to have to be shared with the second disk, and you can imagine obviously the whole system will slow down because of the greater mass and yada yada yada. So again, there are two formulas for angular momentum. I want to point out real quickly that hopefully it was clear from the notes that this equation right here is really only useful if you have a point mass. If you have a mass, a sort of a point object, and that is moving rotationally or orbit, I say orbiting, but it's basically moving in a circular path around another object or a central point. I shouldn't even have to say an object because I'm assuming gravity there, but it doesn't have to be. So the L equals mvr is really only good for a point mass. For large solid objects, we're going to use the L equals I omega. The I is the moment of inertia, also called the radial mass, and again that's a sort of a mass distribution with respect to the axis of rotation. So we got to figure out the initial angular momentum. So let's do that right now. So there is a table of common moments of inertia for solid shapes, and for the I for a disk is 1/2 mr squared. That's a little sloppy there. You'll be given these moments of inertia on a test or anything like that, and you just have to pick the right one. Determining what the actual formula is for the moment of inertia is a calculus issue. So you would not actually be able to determine I, at least calculate the expression for I on an AP test. They would have to either give it to you, or they might ask you for the value of I, but they won't ask you to come up with the expression because that requires calc. Basically integrating volumes and things like that. So anyways, so L is equal to 1/2, and then this is the initial. I'll just put I Li. This is going to be 3.5. R is 0.15. We're going to square it. So the initial angular momentum of the system, survey says, is, that would be the I, and we got to go by the omega. And so the omega it's 15 revolutions per second, so that's 15 times 2 pi in terms of omega. I was wondering why my number seemed too small. So I'll multiply whatever I got by 30 pi. There we go. That's what I got earlier. 3.711 in kilogram meters per second, meters squared per second. All right, that is the total angular momentum of the system. Now we're going to drop another one on there. So the easiest way to do this now is to distribute, let me rephrase that. The total final angular momentum of the system, which is going to be this number, 3.711, that has to be the combined angular momentums of the two objects, right? Makes sense, conservation of angular momentum. So we're going to say I, we'll call it disk A, the initial rotation of disk A, plus I, disk B, rotation of disk B. Now we know that those two are the same, right? Because they're going to spin together. It's a common final angular velocity. So this is going to be the two moments of inertia times their final angular velocity. And again, this is what we're trying to figure out. So now it is really just going to be 3.711 divided by, okay, so now we're going to have these two moments of inertia for the two disks. One will be 1/2, I'll do parentheses, times 3.5 times 0.15 squared. And that's going to be added to the 1/2 times 5 times 0.18 squared. And that is going to be equal to your omega f. When you calculate this all out, let me just crank. I suppose I can just crank it out real quick. So 0.15 squared times 3.5 times 0.5 equals, take that, add it to 0.5 times 5 times 0.18 squared. Take that to the -1 power, but multiply it by 3.711. And this omega is going to be 30.829 radians per second. However, they do want it, well, I don't even know what, but that's going to be in radians per second. If I wanted to divide that, I suppose, by 2 pi, oopsies, 30.829 divided by 2 pi, you're going to get 4.91 revolutions per second, which is, I believe, almost just about half of what the answer key shows. So she's off by a factor of 2. Okay, so now we're going to work on 4. We're going to have a bowling ball moving down the road. We're trying to figure out the magnitude of the angular momentum. Again, there are 2 ways to do this. L equals I omega and L equals mvr. This is not a point object, so a point mass object, so we're just going to not use that one. It's a solid object rotating, so we got to use I omega. Again, we will rely on our chart or table of common moments of inertia. In this case, it's a sphere. So the moment of inertia for a sphere is 2/5 mr squared, and again, that is, it comes down to calculus. So just if you were to try to determine this on your own, it would take probably about 5 times as long as just this normal problem. So you are welcome to do it if you are a fan of calculus, to try to figure out the moment of inertia for this rotating sphere. So anyways, so the L is equal to 2/5 mr squared times omega. And omega is supposed to be in radians per second. So when we do this, we're going to have 2/5 times m, which is 5.5. The radius of the sphere is 0.12 squared. Now omega is 12 revolutions per second, so that's going to be 12 times 2 pi in terms of radians per second. And what you will get, again, it doesn't look that complicated on the surface, but the answer key is going to be slightly off, as you'll see. So times 0.1 squared times 5.5 times 0.4. So L is equal to 2.3886 kilogram meters squared per second. The answer that they gave on the answer key is 0.76, which is exactly off by pi. So my guess is that she just forgot to multiply by pi. And that is how you do this one.